Welcome to the second part of the topic Introduction to Air Traffic Management. In the first part, we have already covered these 5 topics: the objectives of air traffic services, the various units of ATS, the 3 pillars of ATS, that is communication, navigation, surveillance, the various types of radars used for ATS, and rules of the air. So if you have not seen part 1, please go back and look at part 1 and then only look at this, which is part 2. In this part 2, we are going to cover the following topics. We are going to start with discussion on the classification of the airspace. We are going to look at separation minima, then separation due to wake turbulence, increasing airspace availability by using some techniques, and finally we will look at the airspace configuration as displayed on the navigational maps. As I mentioned, this is a very exhaustive topic, so I will not be able to cover all the details, but I will be able to touch upon only some very important and major points of relevance. Airspace organization. There are various types of airspace. Either it is controlled, in which the complete services are provided by the air traffic controller. In fact, operations are regulated by the air traffic controller, and this particular airspace consists of various types of subspaces. There are some prohibited airspaces where you are not allowed to go. There are restricted airspaces. There are airspaces reserved for military use. There are special use airspaces. There are some areas where there are warnings, such as in Pokhran, where lots of testing takes place, etc., etc. Then you have uncontrolled airspace. A large part of the country is under uncontrolled airspace, where there is no authority or control exercised by the ATC authorities. The pilots or the operators, they are the ones who maintain the VFR minimum. Also, if anyone would like to do any flight operations, such as flight of drones or any other experimental aircraft, if you want to test some RC planes, etc., to go to a high altitude, you should do it only in the uncontrolled airspace, because that is the airspace where we don't expect commercial aviation to be operating unless there is an emergency. So therefore, it is very important to keep away from controlled airspace to do any aerial activities. Then there are many categories of the airspace. The categories go from letter A to letter F in controlled airspace, and and G is the category of airspace which is uncontrolled airspace. So I would advise all the students of this course to restrict their activities in only the category G airspace if they want to do any testing. Many colleges have clubs which do, let us say, rocket firing, or they have RC planes, or you want to make airships, fly them, you want to deploy aerostats. Be very careful, because if you do these activities in controlled airspace, you are actually breaking the law of the country. Okay, you are supposed to be under the complete jurisdiction of the air traffic controller when you are in the controlled airspace. You must take explicit permission and approvals. Okay, of course, the controlled airspace starts at some particular altitude. So if you restrict to very low altitude, you might be permitted. But technically speaking, you are not supposed to do any other activities other than the civil aviation, with prior intimation and approval from the air traffic control authorities applicable in your region. In uncontrolled airspace, you have freedom. Here is a map that talks to you about, in general, what is the organization of the airspace. So all the pink areas that you see are class G airspace, which are the uncontrolled airspace. So 400 feet above ground level, away from areas where aviation operations do take place, you are allowed to fly your aircraft. Okay? And in some cases you need waivers. Now, Class A airspace is the most important, and that one is flight level 6000, flight level 600, and starting is at 18,000 above mean sea level, so it will be flight level 180. So in class A airspace, it is completely regulated and controlled. This is the space in which we expect the aircraft to be cruising. So in this area, 18,000 to 60,000 feet above mean sea level, you are completely under the control of the air traffic controllers. Above 600 flight level 600 or above 60,000 feet, you are in class E airspace. Okay, so keep this in mind. Let's see how the airspace is classified. So, as I mentioned, the classification varies from letter A to letter G, and as you move from A to B to C up to G, you have lesser and lesser air traffic control authority, and pilot is increasingly responsible for separation. Okay, in class G airspace, pilot is wholly responsible for separation. You have to have only VFR flights. There is no air traffic control service available in G, in airspace G. The most regulated airspace is class A airspace. In class A airspace, technically speaking, only IFR flights are supposed to operate, but all flights are subjected to air traffic control, and all flights are separated from each other under the direct jurisdiction and the sole jurisdiction of the air traffic controller. So here the pilot has absolutely no freedom. They have to follow the instructions of the ATC to the T. If you are in class B airspace, the rules are same as class A, but the aircraft are IFR and VFR. In class A, we don't expect VFR aircraft, okay? But if they are there, they will be also subjected to the control by the ATC if they are there. In class B, we expect IFR and VFR, both kind of operations taking place. IFR and VFR have been explained in the previous session, so please go back and refer to them. Instrument flight rules and the visual flight rules. Moving ahead, we have class C airspace. Class C airspace is similar as class B airspace, in which if you remember, I said that in class B airspace you will have IFR and VFR aircraft, and information about all of them is provided, plus separation is also maintained by the ATC. In class C airspace, which is one level lower than class B, separation is maintained by the ATC between two IFR aircraft and IFR VFR aircraft, okay, which means the moment there is an aircraft which is operating under IFR, whether the other aircraft is IFR or VFR, the separation is maintained by the ATC. But between two flights which are operating both under VFR, the ATC is not responsible for maintaining separation. The pilots are going to be responsible. Okay. Now, to all the IFR aircraft, you give complete information about other IFR aircraft, but you only give traffic information about other VFR aircraft. So, in class C airspace, VFR pilots get only information. IFR pilots get only information about VFR aircraft, but they are positively separated with all other aircraft, whether IFR or VFR. But if there are VFR and VFR2 aircraft, the separation is not the responsibility of the ATCO. Going to class D, again one step lower. Now we are only concerned about separation for IFR to IFR flights. The ATC responsibility is reduced to providing separation only between two IFR aircraft, and for all the other aircraft, whether IFR VFR or VFR VFR, you are only supposed to give traffic information. As you can see, the responsibility is getting diluted and more responsibility is being passed on to the pilots. Proceeding further, you have class E airspace, which is same as class D airspace, except IFR flights are subjected to ATC and separation from the IFR flights, and all other flights are going to receive traffic information, but only as far as possible. In class D airspace, provision of information is mandatory, but in class E, information will be provided only if it is possible, if the ATC is able to handle that workload. Okay. So, the primary responsibility of the ATC in class E airspace is the IFR aircraft and their separation from other IFR. Other flights, they will receive information if possible. And then you have class F airspace, which is same as class E, except now all IFR flights, they receive only traffic information. Okay. Separation is not the responsibility now, and for all flights you are only going to give flight information service, and that too only on request. And finally, if you go to class G airspace, you are in an uncontrolled airspace. Only if requested, flights will receive flight information service. Otherwise, there will be no control exercised by the air traffic controller. The complete responsibility of separation is that of the pilot. So, as we have seen, when you go from A to B to C up to G, the authority and the control of the ATCO reduces, and more responsibility is passed on to the pilot. Let us have a look at now how ATCOs maintain separation minima between two aircraft, whether they are at same level or they are at converging paths or one behind the other. So, the first separation is vertical separation. So, above flight level 290, that means 29,000 feet, when you fly above that altitude, then between two aircraft which are in level flight and in opposing directions, there is a minimum vertical separation of 2000 feet or 600 meters mandated. Okay. Now, this separation can be reduced. I will talk to you about that little bit later. Below flight level 290, the separation is reduced to about 1000 feet or 300 meters. Okay. So, flight level 290 is the cutoff. The reason for this is that most aircraft are going to cruise at flight levels above 290. Okay. So, therefore, at that location you can give larger separation. When you are below flight level 290, you have more accurate information available about those flights because of the radars that you have, and therefore the separation minima is reduced to 1000 feet. Now, even when you are at above 290, as I mentioned, there is one operating scenario called as RVSM, that stands for reduced vertical separation minima, and we will talk about it in more detail separately. There, because of the presence of very accurate navigation equipment and because proactively we know the location of the aircraft more accurately, therefore the separation minima have been reduced to 1000 feet. This allows traffic to, this allows much more traffic to be handled by the ATCO. It increases the throughput of the airspace. This is RVSM. In non-RVSM, you have to maintain 2000 feet. So, if the aircraft is flying from east to west at flight level 290, the next aircraft that will be flying in the same direction would be only at flight level 330. Okay, because between 290 and 310 you have 2000 feet, and so two aircraft which are flying at the same direction, they will have a separation of at least 4000 feet. Okay. But if you go into RVSM, you are introducing more levels in between, and you can see how the traffic capacity can be increased. Okay. But this is not very easy and available to everybody. You need to have some very good instrumentation on board the aircraft to be able to operate under RVSM. You must have two independent altitude measuring systems working. You must have an SSR altitude reporting transponder. That means the one that connects, which communicates with the secondary surveillance radar and gives the altitude information. Then you need altitude alert system, you need an autopilot, you need flight crew to be trained under the appropriate category by some training programs. Then minimum monitoring requirement is you should have minimum 2 aircraft for 1000 hours or 2 years. So this is regularly monitored, and if it is established that the incident free operations are there, then the extensions are given. So as I said, we will look at this more detail later on. Moving ahead at the horizontal separation. So you can have it radial. So whenever there is an instrument called as a non-directional beacon, it can give you radial information. So therefore, the minimum separation between two aircraft which are having crossing paths at an NDB, it will be 30 degrees separation. Okay, and from the instrument from the NDB, the aircraft has to be at least 15 nautical miles away. On the other hand, if you have VOR, which is a more sophisticated equipment, then the separation angle is reduced to 15 degrees. Okay. The distance remains the same, but the angle reduces. This is because VOR is much more accurate compared to NDB. NDB is a non-directional beacon. Okay, it just transmits the beacon 360 degrees. VOR is little bit more accurate. Moving ahead, if you want to look at lateral separation, that means aircraft flying at the same route at same level, there should be minimum 15 minutes of gap. You will not see any aircraft at exactly the same altitude behind another aircraft within a gap of 15 minutes. Okay. Now, when the navigational aids are present that permit very frequent position updates, then it can be reduced to 10 minutes. Okay. And in terminal area, where you have far more accurate information because of the presence of the radars, you can reduce this to 5 minutes, but still 5 minutes is the minimum. Now, nav aids are permitting lower separation. So, for example, in a normal scenario, 15 minute separation reduces to 10 minutes if you have navigational aids along the route which give you frequent update. And again, if you have a crossing routes, you have to have 15-minute gap, but if there are navigational aids available at both the places, it can be reduced to 10 minutes because you get frequent updates. There is another important criteria for separation, which is because of the wake turbulence. When an aircraft flies in the air, it creates a huge amount of turbulence behind it. The turbulence is mainly because of the swirling of the vortices at the wing tip. Okay. So, therefore, a small aircraft behind a large aircraft is going to be subjected to a lot of disturbance and even dangerous downward draft. So, therefore, there are some wake turbulence categories. Aircraft which are less than 7,000 feet, they are considered to be light aircraft. Okay. Between 7,000 to 136,000, they are considered to be medium aircraft. Okay. Then there are heavy aircraft are more than 136 tons, except some which are considered to be super heavy, such as Airbus A380, AN225 and AN125. These are super heavy aircraft. The max takeoff weight of AN225 happens to be 650 tons. Now, one more category has been introduced between medium and heavy, and that is called as large. So, for large, FAA has introduced a category more than 19,000 and less than 140,000, that will be called as the large category. So, there is an exception depending on the aircraft configuration characteristics, there is an exception. Now, Boeing 757 has a maximum takeoff weight of only 116 tons. So, it should actually come under the large category, but it is found that the wake turbulence behind a 757 is very large, and therefore, it is considered to be heavy, not large. So, the wake turbulence behind a Boeing 757 is as much as what you see in heavier aircraft, and therefore, it is an exception. Now, there has been progress in this area, because if you actually look at wake turbulence and if you look at the separations, there are severe constraints on the capacity of the airport. Okay. So, over the years research and operational testing has been carried out to look at the recategorization called as RECAT. Okay. So, this has happened both in the USA under the FAA and in the EU under the JAR. The phase 1 was started in 2013. Here the wake turbulence categorization was based on the takeoff weight and liftoff speed, wingspan and the trailing vortex strength. So, the categories were created as super, ultra heavy, ultra light, light and small. In phase 2 which was in 2014, one more category was introduced which is separation based on and also separation based on pairs. Okay. So, like 747-100 versus A321, what should be the separation? So, now you are looking at coupling between two specific aircraft. Phase 3 was launched in 2016 where the conditions of the atmosphere were also factored in. Okay. Now, in the European Union, the RECAT 1 was done in 2016. Here you have light, ultra medium, LM, ultra heavy, all these categories have been created based on extensive database of information. RECAT 2 was launched, same 6 categories, but now we look at separation based on special pairs. RECAT 3 is going to use real time data to decide separation. So, now we are going to fix instruments at the airport which will be dynamically measuring the turbulence and deciding based on the actual turbulence values how soon the next aircraft can be released. So, you can have a lower separation. Okay. Suppose you have heavy winds, they will dissipate the turbulence much quicker. So, we will have lower separation. So, till we achieve those criteria, currently the separation is either based on distance or kilometers, okay, distance behind the aircraft. So, if you have a super heavy aircraft, then a heavy aircraft behind it has to wait for at least 5 minutes, 5 nautical miles, I am sorry. The medium aircraft has to have a separation of 7 nautical miles and light aircraft 8 nautical miles. Similarly, if it is a heavy behind a heavy 4 nautical miles, medium behind the heavy 5 and light behind heavy 6. So, like that some separation minima in distances have been created, but you can also have time based separation minima. This is very much useful at airports. So, let us say there is a departure of a super heavy aircraft. Behind that, if you want to release a heavy aircraft, you have to wait for minimum 2 minutes, because studies have shown that within 2 minutes the turbulence of a super heavy aircraft subsides to a level that can be handled by a heavy aircraft. But if you are a medium aircraft behind a super aircraft, then you have to wait for 1 more minute, and if you are a light aircraft behind super aircraft, you have to wait for 4 minutes. If you are a medium aircraft behind a heavy aircraft, then 2 minutes is enough, but if you are light, you need 1 more minute. So, light aircraft require more time behind heavy and medium aircraft, and behind super they require 1 more minute. Okay. Now, let us look at how we can increase the airspace availability by partitioning the airspace. So, this is the conventional separation, one level of vertical separation and horizontal separation, but you can actually have composite lateral and vertical separation. So, you could increase the throughput by bringing in 1 more layer in between, which is at half the distance. Let us look at the configuration on maps, because when we look at navigational maps, the routes are marked in a particular way. So, very briefly we will look at a few cases. So, assume that there is an area which is just around an airport. What you see here are the holding patterns approved and also the arrival and departure, the arrival path to be followed. So, the area around the small airport which comes under the control zone of the approach controller, and then there will be an area which will be coming under the control of the area controller. So, it looks like this in the side view, but on the map it will be depicted as two concentric circles with the airport point marked in the center. Now there could be two neighboring airports, both of them are being controlled by the same area control. In that case, you will see the depiction will be in this way. Notice that the area control has a minimum altitude higher than 0, higher than ground level, whereas when you have the aerodrome control, then the space starts right from 0. So these two airports, they have their own holding patterns and arrival and departure patterns. They will be depicted as a big circle showing the area and two concentric circles. Similarly, if there are some routes and there are 3 airports in the vicinity, these routes will be shown in the chart like this. You can see in the side that you will see passages like this, which will clearly indicate that these are the routes which are to be taken by the overflying aircraft, and also the aircraft that take off and land at these airports are going to follow a particular profile. Similarly, if you have 5 airports, 3 nearby and 2 little bit away on the routes, this is how the charts will be indicated. So as I mentioned, this is a fairly complicated subject regulated by law, and therefore we cannot actually go into depth. So this should be sufficient for you to get an appreciation of the basics of air traffic control. Thank you for your attention.